Can you hear from my voice? Can you see the screen? Can you hear from me? Can you see the screen? Can you hear? Can you see the screen? Okay. Okay, it's now 10 minutes past the 6:30, so I think we better start the lesson. Just to make sure that you have hear my voice and also the screen, please respond me by typing yes in the chat room, please. Okay. Good evening, everybody. Now we'll start, continue our lecture 4, right? The lateral earth pressure. Now we want to do a little bit of revision in the lateral earth pressure, right? Just to recap your concepts. Now, lateral earth pressure. Okay. Now, for a retaining wall, we have a ground surface here and also the bottom of excavation. Now, take a look on this stress element, this soil element, right? Now, before the excavation, in other words, before we remove the soil in front of the retaining wall, what's the initial stress? Okay. Now, what's the initial stress there? You got the what? The sigma Z, right? The vertical stress and also the horizontal stress. So that is sigma Z, and that is sigma 0. Okay. The horizontal stress is sigma 0, and the vertical stress there, sigma Z. Now, here you got, say, sigma Z is greater than sigma 0, right? Or sigma naught. So you got here, right? That is the normal stress, and here's the shear stress. Okay, sigma is at greater than sigma naught. So we got this point, sigma is at, and here sigma naught. Okay, so you can draw a Mohr circle to represent that state of stress for that soil element. Now, that's the original state, right? Now, after we remove, say, stage 1 times 0 here, stage 1. So when you remove the soil, right, the soil out of the site, in other words, you are doing an excavation, what will happen to the sigma 0? Will become what? Smaller, right? So sigma 1 becomes sigma 1, which is smaller. So you got what? This small circle, right? Sigma 1. And then you continue the excavation, okay? So up to here, right? Stage 3. So you got a smaller, much smaller sigma 3, right? Sigma 3. In other words, you got a greater Mohr circle, right? Because sigma Z remains constant, the horizontal stress decreases from sigma naught to sigma 3. Now, if this Mohr circle, right, that's Mohr circle for sigma 3, right? This Mohr circle for sigma 1, and that solid More circle stand for sigma naught. Now, if that more circle free is under this more Coulomb envelope, right, then the retaining wall just stay there. But what about if now if the sigma tangent phi, okay, now if this small circle touches this straight line, shear strength equals to cohesion plus sigma tangent phi, then the more circle free reaches active state, right? Then the sigma free become the active pressure, right? Active pressure. In other words, sigma A is equal to the lateral pressure coefficient times sigma Z, the vertical stress, right? The active pressure coefficient is equal to the ratio, right? The sigma A over sigma Z. Okay, so we have the soil here at the back of the retaining wall is now at the active state. Okay, and the retaining wall is going to move out. Whenever the retaining wall is moving out, right, into the excavation site, that retaining wall is in an active state. Okay, and at that time, the more circle just touches the more Coulomb envelope as indicated by this blue more circle, right? Touching at the point. Okay, so that is the story, right, for the active pressure. Remember, the more circles start to develop, right, from the more circle 0, 1, and 3 until it touches that failure, string envelope. Okay, now, in other words, the retaining wall is moving to such an extent that the active pressure could be fully developed behind the retaining wall. Now, that's the story for the active pressure. Okay. Now let's come to another story, the passive pressure. Okay. Now for the passive pressure. Again, this retaining wall. Right. So that's the ground surface, and that is the excavation site. Now, if the wall is going to move in, so inwards. Now consider again this element, soil element, right? Now this soil element, okay, again you got what sigma is that? The vertical stress, and that is the horizontal stress, right? Okay. Now, if you draw, okay, that is the shear stress, and that is the normal stress, right? Now, the original stress, sigma naught here, right? And that is the sigma z, okay? Now, if you draw a small circle, that is the original state, right? Before the excavation or before the wall is moving in, right? So you have a very small, more circle. Now, sorry. Now, by the time the wall moving in, what will happen? This sigma 0 will become larger and larger. So until, okay, greater than sigma 0. When you increase, right, the horizontal stress because of the passive state, because you are pressing the wall against the soil, so the sigma naught will be increasing, right, from sigma naught to sigma 1. So you are going in that direction, right? And then sigma 2 until you got sigma 3. So again, so that is sigma 1. You know, that is sigma 1. And then you sigma 2. And then you got what? Much greater sigma 3, right? Because your horizontal stress is greater and greater. Now, if you draw okay, that's C, that's phi, and that is the string envelope, C plus sigma tangent phi, right? Now, if you, that more circle 3, touches this envelope line at this point, then the soil comes to a passive state, okay? And probably this soil is going to move upwards, or in other words, it gives you some upheaval of the soil surface. You know, in the active state, you have the ground subsidence settlement, but for passive, because the wall is pushing, right, the soil wedge upwards, so the ground surface will become elevated, right? Will become upheave. So we have this passive state. Now, the sigma 3, right, the horizontal stress, over sigma naught is the passive pressure coefficient, right? Remember, it's always the horizontal stress over the vertical stress, okay? So sigma Z, right? Sigma Z. Sigma 3, right, will increase from sigma naught, sigma 1, sigma 2 until sigma 3. Okay, you got this concept. That is the coefficient of passive soil pressure. Right? So that is the passive state. So in other words, the Mohr circle, if the Mohr circle is going on the left-hand side, that is the active state. On the right-hand side, it gives you the passive state. Okay. Let's come to the checkpoint. So you got the idea, right, or the concept between the active state and the passive state. Is that clear to you? I want some response from you. Right? Is that okay for all of you? Only one got yes. What about the others? Okay. Not too many. Some others have the reservation. Is it because that you don't understand the lecture? I always want to insert some checkpoints so that I want to know whether you understand before we continue. Okay? It's important to have the checkpoints here. Example 2. Okay, let's just hang out for a while first, right, before we step into example 2. Because I want to continue my lecture on the concept of the passive and the active pressure, okay? Now, important formulas. Now, for active pressure, you got this equation. Sigma A for active, Ka times gamma Z, right? Gamma is at the vertical pressure. So you multiply the active pressure coefficient to get the active pressure, right? But remember, for cohesive, for C5 soil, you should remember the cohesion, right? And that's square root Ka. Now, what's Ka? 1 minus sine phi over 1 plus sine phi. Okay? Now, this is a very important equation. And what about for passive? Passive pressure is equal to Kp, right? Kp gamma Z plus, right, 2c square root Kp. Now, what's Kp? The other way around, 1 plus sine phi over 1 minus sine phi. Okay? Now, that is the most important lateral earth pressure formulas. Okay? It's not difficult to recall this formula, or memorize this formula. Active pressure equals to Ka times gamma Z minus. Remember, active pressure is smaller. Passive pressure is greater. So minus 2c square root. Remember, square root of Ka. What's Ka? 1 minus sine phi, 1 plus sine phi. Again, this is smaller compared to the Kp, right? Now Kp, 1 plus sine phi over 1 minus sine phi. So Kp will be, is always greater than Ka. And for the passive pressure formula, remember this should be plus, not minus. Now, of course, in your notes, tangent, right, square, sorry, plus 5 over 2 minus 2c tangent 45 degree. Okay, and here gamma Z, sorry, gamma Z sorry, I made a mistake there. That should be minus. And here, plus 2c tangent 45 degree plus 5 over 2. Now, it's just the same, right? But I will prefer to record the formula, right, in terms of Ka and Kp, rather than, it's quite difficult to recall, something like that, right? Tangent square 45 degree minus 5 over 2, and so on. So can you take a photo of this PowerPoint? Because I think it should be also as a supplement to your lecture notes. Right? I like to record, the formula in terms of Ka and Kp, while Ka is equal to 1 minus sine phi over 1 plus sine phi, and so on. Okay. So any question for this formula? Okay, is that okay for you? Now let's take a look for the example 2. One of you asked me to redo the example 2. Okay. Example 2. Where's example 2? Okay. Okay. Now here, because it's the active pressure, right? You know that's active. So you have to use this formula. Sigma A equals to what? Ka gamma Ez, right? Minus 2c square root Ka. Is that correct? Now here, because for this point, the pressure is equal to 0, right? So at this point, sigma naught, so 0 equal to Ka gamma Ez naught minus 2c square Ka, right? Sorry. That's, Ka, Ka, right? So what's Ka? Can somebody tell me what's Ka? Ka here, right? Ka equals to what? 1 minus sine 26 over 1 plus sine 26, right? So you got your Ka. So Ka is equal to 0.39, okay? .39, okay? So in other words, Z naught equals to what? 2cc is equal to 8, right? Square root 0.39 over Ka 0.39 and gamma 15, okay? So you got 1.04 meters. Now, what about for Z equal to 0? When Z is equal to 0, so it means at the ground surface, right? How is that value come from? When you put, the Z equal to 0, right? Say sigma 0, Z equal to 0. So this one is 0 because Ka gamma Z equal to 0, so Ka gamma Z equal to 0 minus 2c C8, right? And square root Ka. So it should be a negative value, right? It should be equal to 6.09 kPa. Okay, negative. What does the negative value mean? It means the soil under tension, not under compression. So under soil tension, sometimes called suction, right? 真空啊，即係低過一個大氣壓力。So it's below the atmospheric pressure, right? So suction. Okay, that explain how the suction value coming from. Right? And what about here? Well, at that is that equals to what? 4 meters, right? Is that equal 4 meters? So sigma is at the bottom, right? Bottom equals to Ka. Ka is equal to 0.39. Gamma. What's gamma? Gamma 15, right? And then what's the Z? Z equal to 4, right? Minus 2 times 15 and square root 0.39. Now it should give you 17.31 kPa. So we got what? At the top, negative 6.09, right? Here. And at the bottom, you got 17.31. And Z naught equals to 1.04, right? And that one will 4 minus 1.04 give you 2.96. So we got, right? We got the complete pressure diagram. So is that clear? What about one way? You ask this question. Okay. So everyone happy with the explanation for this example? Now let's continue the calculation for the active force. Okay. So what's the total force here? What's the total force? So that's F1. F1 equals to what? 17.31, right? The area of the triangle, right? Times 2.96 divided by 2. It gives you this area, right? The area of the triangle, right? Base times the height divided by 2. Okay? So you got the F1. And what is the position of F1? 2.96 divided by 3, right? That gives you kilonewton per meter length of the wall, and that is, it gives you 2.96 divided by 3 meters, right, above the bottom of the wall. Okay. What about for the upper triangle? Now you have to be very careful about this triangle. Why? Because if soil cracks by tension, you know the soil cannot resist tension, right? So the soil will simply be broken into two parts, right? So you have the tension cracks here. You know, the soil cannot resist the tension. So that is the Z0. Now, if the soil cracks, that means all the tension will be lost, right? Will be lost. There will be no tension at all. So you just having you are just having the green triangle there. In other words, the total force acting on this retaining wall is simply equals to F1. Okay. Now, depending on the question, if the question here after the tension crash occurs, in other words, this F2, you should ignore this yellow triangle, right? There should be no force, no tension to be developed above, right? The tension cracks, about the depth of the tension cracks. Is that okay? Okay. Now, the question also asks for what's the passive pressure developed? In other words, if the wall is not going out, but going inwards, in other words, this wall is going inwards, right, towards the soil, right? The wall is moving towards the soil. Then you have to calculate the passive pressure. Okay. So sigma P equals to what? Kp, right? Gamma Z, remember, 2C square root Kp, right? Now Kp is equals to what? Here, 1 plus sine 26 minus 1 minus sine 26, right? Equals to what? 2.56, right? Here, right? 2.56. So 2.56, okay? So here at the top and also at the bottom, at the top, what? Is that equal to 0 plus 2C? C is equal to 8, right? And then square root 2.56, right? And what about the bottom? Kp 2.56, gamma, what's gamma? gamma equals to 15, right? 15. Right? Times Z. What is Z? 4 meter, right? 4 meter. Plus 2C, again, 2 times X, 2.56. Now that will give you what? 204.8, right? Two o 4.8 kPa. Okay, and sigma naught at the top equals to 51.2, right? Sorry, here it should be C equals to at the top. Oh, sorry, I forgot the surcharge, right? That should be a surcharge. Sorry for that. So I forgot this one. So you should here, right? The surcharge. Sorry, I forgot the surcharge. It's plus Q, right? So I forgot the surcharge. Can you hear my voice and the screen? I think the system has been down, right? So I have to log on the computer again. So can you hear from me and also see the screen? So all of you can hear and see the screen, right? I see. Okay. Okay, can you see the screen? So back to normal, right? Okay. Sorry for that. I think I don't know why the connection is just offline, right? So I believe you will be able, right, to work out the forces, right, from this pressure diagram. Just work out the area of the rectangle. Of course, for the trapezium, you have to divide the diagram into two pieces, the triangle and also the rectangle, right? And work out the area of the triangle and the rectangle, and also locate the centroid, right? And then you apply, the moment, right? The force times the lever arm, right? To work out the centroid, right? So that is the whole calculation. So is that okay? It's not that difficult, right? Okay, you want to know somebody want to know how to find out the H1, H2. It's quite straightforward. Now here, right, H1, now the area of this rectangle, sorry, right? Now tell me what's the centroid of this rectangle, right? It should be in the here, right? At the middle, right, of this rectangle. If the rectangle is 4 meters high, so H1 must be 4 meters divided by 2, right? Okay. At the center of the rectangle, because that's 4 meters, right? So here, H1 should be equals to 1/2 of the height of the rectangle, right? And then for H2, we are talking about, this big triangle. Now tell me what's the centroid. The centroid is here, right? You know the centroid of the triangle is equal to 1/3, right, of its height about the base, right? So H2 is equal to 4 meters times 1/3, right? So that is the centroid of the green triangle. So okay, Mr. Zhong? Okay. What about for the others? Are you happy with the calculation? Or are you happy with my explanation? Now, you may study the explanation given in the lecture notes, but I want to explain, right, my will or my method of how presenting the calculation or how the calculation will be carried out, right, step by steps. So I think all of you should acquire, right, the procedure of carrying out the calculation for the, the forces, right, from the pressure formula, right, from the, this very important, formula. I try to demonstrate, right, how to use this formula. Okay? Now, somebody may ask, what's that? Why is it so? Okay? Now, let me take some time to explain, right, this concept. Okay. Let me insert a new slide there. First of all, you have a active case, right? That is the retaining wall, right? Now, take a look at the Moore circle. Remember, right, this soil element, if you enlarge it, this soil element, the sigma is that, and here is the, the sigma A, right? Now, here you got the envelope, right? That is the, the sigma A, and that sigma is that, right? Now, that is, the 2 theta, right? More circle, 2 theta. Now, what does that mean? It means that here, from the sigma z, you turn anti-clockwise 2 theta. That will give you the failure, right? Because it fails here. Fails here, right? Where is the sigma z? Here. That's the plan, right? You turn anti-clockwise, right? Anti-clockwise. It means here, right? anti-clockwise, theta, right? Here is 2 theta, but for in more circle, you have multiplied the angle by 2, right? 2 theta. In anti-clockwise, that will give you the failure plan. In other words, when you draw here, that gives you the failure plan, right? So what's this angle? Again, theta, right? Because d theta is equal to d that theta, so that is theta. Now, what's theta? Come on, what's the theta? Let's draw here. What's that? That is 5, right? Because here is the Coulomb, more Coulomb, sigma tangent 5, right? So what's the angle? 2 theta equals to what? The sum of the interior angle should be equal to the exterior angle. So 2 theta is equal to 90 degrees plus 5, right? Okay, therefore, theta equals to, right? Okay. So here is equals to, okay? If you draw and again you got the complete Mohr circle, right? And here, right? You got here. Okay. So what about for this point? Now it gives you the other set. Sorry. So again, you got, this here, right? Okay. So here, clockwise 2 theta, right? Again, you got here, right? Theta, right? So in other words, the soil here will fail in 2 sets of the failure plan. Right? That's why for the active pressure, right, here, for the active pressure, the soil wedge, this soil wedge will fail along this plane at 45 degrees plus 5 over 2, right, to the horizontal. What about for the passive case? Say for passive. Now for the passive, okay, here, sigma is that, right? You got a passive pressure. When it touches here, right? Okay, so you got what? It fails here. Okay, and you have the clockwise, right? 2 theta. And here, two theta plus what? That's 5, right? 2 theta plus 5 equal 90 degrees, right? Theta is equal to what? 45 degrees Sorry. Therefore, theta equals to 45 degrees minus, right, 5/2. In other words, for the passive case, if the wall is here, the wall is moving out, right, to develop the active pressure. For the passive, it's moving in. So this soil is a soil wedge, right? The soil wedge is going to what? Try to slide upwards, right? While for here, when the wall is moving out, this wedge will slide down, right? So that is active case. But for passive, the other way around. And what's this angle? That should be what? 45 degrees minus 5/2, right? So the slipping line, right here, the slipping line. Okay? So the other set of the slipping lines will completely different, right? Between the passive case and active case. For the active case, 45 plus 5/2. For the passive case, it's 45 degree minus 5/2. Now, all these can be derived from the interpretation of Mohr circle, right? Whereas with respect to the, the string envelope. So for this case, it's active, right? So that is active case. So coming back to this, before we go further, let me take a check. So you understand my explanation? So are you happy with the explanation? For the angle of the failure surface, is that okay for you? No? Can you see the screen? So do you understand? So yeah, you understand the angle of the failure surface, okay? We just read, right, the data or the calculation from the Mohr circle. What about the others? It appears only a few of you understand my explanation. What about for the others? if you do not have further question, then I will continue my discussion for the retaining wall. Right? If this at the top of the wall, the ground surface is not horizontal, but it's a sloping surface, an angle beta, right? Angle beta. Angle beta here, beta. Now, if the slope surface is set beta to the horizontal, then we can draw, right, the failure surface, an angle here, right? We have just proved that. When this when the movement is going out, so it develops the the active pressure, right? The active state. And the passive state, again here, we have learned that it should be 45 degrees minus 5/2, right? If the wall is moving inwards, that will develop the passive condition. Now, ranking active pressure theory for this sloping surface, right, behind the retaining wall, the assumption is that the active pressure here, right, will not be acting normal to the back of the retaining wall, but it will parallel to the sloping surface. Okay? So what you have to do, again, you have to work out the, the pressure here, Ka gamma H, right? But the direction, please remember the direction here, right, will be at angle beta, parallel to the sloping surface. And for this, pressure diagram, to triangular pressure distribution, again, the centroid is again equals to 1/3, right, about the height, about the bottom of the wall, because, still, this is a what? A triangle, right? The triangle. The centroid is at the 1/3 about the base of the bottom, about the base, right? About the bottom. Okay, so there's nothing new, right? Except that we have learned that the direction of the force and the pressure will be parallel to the sloping surface. Okay. Even for the inclined back here, inclined back, it means the wall here, right? The wall here is not, a rectangle, it's a trapezium, right? The front face is vertical, but the back face is sloping, right? A sloping, the back is the sloping surface to the retaining wall, right? So you just draw a vertical line there, right? disregard, right, the sloping back, and then you here measure the height, not this height, right, but a greater height, slightly greater, right, because here it increased by this bit, right, because you have the point here, so the height of the wall appears a little bit higher, and then from there you calculate, right, the active pressure for a greater height, right, not the smaller height, a greater height, right. What about the pressure formula? Well, it looks very complicated. Right? Now you don't need to memorize this formula. It will be given, right, as a formula, right, in the appendix. Whenever you are coming across an examination or test, you will be given this formula. And beta, the beta is the the slope, the angle, right, of the sloping surface at the back of the retaining wall, right, beta. And phi again is the the angle internal friction. Now, of course, if you let beta equal to 0, in other words, that retaining wall is no longer sloping, is horizontal. Now that Ka will give you back 1 minus sine phi, 1 plus sine phi. Okay, there's nothing new. It could be restored back to the the formula we have learned, right, for a horizontal ground surface. So again, you can use this formula, right, because here, right, if you got H, so the active pressure Ka gamma H, so you got this force P is equal to Ka gamma H times H over 2, right? The area of the triangle, right? So that's why we have this formula. Now you don't need to memorize it, but you have to know how to work out from this triangle, right? So once you know the pressure and the height, right, you can calculate the area of this triangle. And for passive, again, you have the other form of the formula, right? Again, the lateral force is given by half gamma h squared, but here the Kp, because we are talking about the passive pressure condition. Now it will give you back, right? If you set beta is equal to 0. Well, for the example 3, right? We want to work out the, here, right? The force acting behind this retaining wall, depending on the, here you work the active pressure, right? Here, right? You want to get the active pressure. So very simple. You just, beta 20 degrees, right? And the phi 34 degrees. So you input everything into the formula. And you got Ka equal to 0.338. And then you work out the, the force, right? Is 1/3 of the 7 meters give you 2.33 meters, and the the total force will be acting at this point, and the direction again should be parallel to the sloping surface, right? 20 degrees to the horizontal. Okay, that finishes up our chapter 4. Is it okay for you? I like more feedback from you, not just a few of you. It's not good enough for me. I don't want to talk to the air, right? To the voice. I want feedback from you. Okay, thank you. So any question about the lateral earth pressure? It's a very important topic, in fact, and it is also a milestone development in the soil mechanics, the horizontal pressure, because anything move horizontally is a completely disaster. Imagine a retaining wall, right, topple over, right, tilting over because of horizontal force. For a building, what's the horizontal force? The wind load, right? So anything anything connected with the horizontal movement is a very catastrophe，一個災難性。So that's why the engineer will be very careful in dealing with the horizontal force, particular, the location of the horizontal force. Despite that, it's not much, but it's acting a very great height. Now that will give you a very great moment, right? Because the moment is equal to force times the distance. Okay, even though the force is not that much, but the height is very important, right? You imagine a tall building, right? A deep basement that will constitute a very great moment. And the building is very thin, right? The wall is also very thin, so they may not resist the bending moment, right? So the structure may be broken into pieces, right? Due to the horizontal force and the great horizontal moment. So any question about this chapter? No? It looks like you understand everything. Now, if you don't have any question, I will have one for you. Here you got a wall, okay, and you have a a ground surface, and then you have a a prop. You know what a prop? Okay, it's a member, right, to stop the overturning, and you got the base here. And suppose that the height of wall is 5 meters, and you got c equal to 5 kPa, and gamma equal 18, and everything, right? The phi 30 degrees and so on. Okay, so by theory you can calculate this. You have the Ka, gamma Z, and so on, right? So you got the active pressure, pointing towards to the left, and then you can work out the force here, right? Acting in the opposite direction. Okay. So suppose, according to the earth pressure theory, right, you can work out is 100 kN. So you are happy with that after very careful calculation. But what about here? You got here 8 meters, right? And again, you got the ground surface. Again, you have that type of soil, 5 kPa, and gamma 18 something, and phi equals to 30 degrees, and so on. And then you work out the propping force, right? Okay. Suppose you got 200 kilonewton. Okay. But now, if the basement, the base of this basement is looking like that, now tell me, and that prop is the same prop, right? Here you have the same prop here, right? Tell me the prop force equals to 200 or 100 kN. It's the same prop there, right? Can you tell me you should take 200 as the maximum propping force, or u equals to average of these two values? Any idea? What's wrong with the calculation? In the previous working example, we have just ignored the other side, right? Just concentrate, the force acting on that wall only. You just ignore, right, what's happened on the opposite side of that wall. But in the basement, you got two walls, right? Confronting each other. They are facing in the opposite direction, right? They are facing each other. So what's the force in that prop? So you understand my question, do you? $200 kilonewtons, the force. On the left-hand side, the force in the prop is 200 kN, because it retained a greater height, 8 meters, right? On the right-hand side, the prop just retained a wall of height 5 meters only, so the force will be smaller, right? So that's 100 kN. I will tell you that's the most difficult part, right, in the soil mechanics compared with other structural mechanics. You cannot concentrate on one part of your structure only, right? You have to consider the whole thing, right? So you have to apply the integral approach, right, to see, right, the interaction between the left-hand side and the right-hand side. Ignore the other side only. So that is, the approach adopted by the geotechnical engineer, the interaction between, the individual parts of the geotechnical structures. So that's the point. Okay. Before we leave this chapter, any question? Okay, I will go to another new chapter. Okay. Chapter 7, slope stability. Now, at the end of this chapter, you should be able to appreciate, right, how the slope will become stable or unstable, or any failure will occur. And then you have to use some methods, right, to analyze the slope stability to prevent or to know whether it will fail or not. And finally, you should know something about the different means of protecting the slope. Okay. The slope will fail just because of the gravity. Right? The gravitational pull will try to pull a very large mass of soil down the slope, particularly if the slope is very, very steep, right? Because the soil mass is assembly of granular material. You are placing individual objects, right, over each other, and you form, a whole mass of, the particle packing each other. But when you are packing those particles to such a great height, now that may trigger off, right, a large scale of sliding down failure. And anything in the upper part sliding down while over the, the bottom part, that is a shear case, right? So that's why we have to study the shear strength of the soil, because soil always fails by shearing. In other words, the soil mass will always slide against another soil mass. So that constitutes a shear between the two masses of soil. And the potential failure of the soil slope may be caused by several means, right? Whether the slope is too steep, or you may have groundwater problem. The groundwater, inside the slope may try to come out and push the soil downwards. So groundwater is the chief enemy, right, behind any slope failure. And also any slope surface properly maintained should be safer than those slope without regular maintenance. Particular any the blockage in the surface channel where the rainwater could be, block off, right, and cannot discharge downwards. So there will be large amounts of rainwater seeping into the soil, and that will give rise to the groundwater table. Now that will trigger off the soil slope stability. And sometimes, in Hong Kong, we have at the top of the slope, you may have some buildings, or even you may surcharge the slope by, by stockpiling the construction material or anything, right, on the top of slope. So you are surcharging it. So you are loading on it. That will also constitute another important cause of the slope instability. Now, there are some terms you have to learn about. Cut slope means you are cutting some soil out of a soil mass. So that is a cut slope. In other words, say if the original ground is here, and then you are do some excavation, right? And then you remove the soil away so that you can build a building there. Okay, so that is a cut slope. So you are removing these pieces of soil, right, away. So that's called what? Excavation. Because you are removing the soil out of it. What about for the soil slope? Here, you have the original ground here, right? And then you put up a soil there to give you a flat piece of land so that you can build your building there. So that is the field, right? Field slope. Field, right? Field slope. So you are filling a platform, right? Filling a ground platform, right? Now in Hong Kong, we do a lot of such activities, right? By, to get pieces of land from the slope, or sometimes you have to set up some platform, right? Some horizontal and flat platform by filling the ground, right, with the soil material, by importing the material so that you can get a flat piece of land. So in Hong Kong, we have cut and fill, right? Particularly here, right? You have the original ground there. Then we want to form okay. So you got a cut there and fill there. Right? So you have the, put this cut into the fill. So you balance the cut and fill. So you don't, you are trying to use the material there, right? You remove the material and then fill the other spots of the area with that material. So you balance the cut and fill. So that is a quite a good and economical way to do that, right, in Hong Kong. So you have the cut slope, right? That is the cut slope. That's cut slope. And here's the fill slope. Okay. Now these two slopes are man-made slope. Of course, if you don't uh, do any works on the slope, it's a natural slope. So that's the natural slope. So then natural slope, right? It's completely untouched. Now for the slope ratio, we are talking about 3:1. Okay, 3:1 or 3:1. It means that so 3:1, right? 3 horizontal and 1 vertical. Okay. And then the toe here, the toe of the slope and the top of the slope. Okay. Sometimes it's called the terrace, or sometimes it's called a berm. Okay. We more use the berm rather than terrace in Hong Kong. And the slope surface, okay, and the slope height. What's the slope height here, right? The height of slope, the vertical height of the slope, right? So it's equal to the difference in the elevation between the top and the toe of the slope. Why do we need a berm there? Why we have to do a berm there? Simply for the maintenance, right, of the slope. So you got a surface channel there, so the guy could come up, right, and then do the cleaning of the surface channel, the surface channels. Whenever any rain pouring on the the slope surface, the rainwater, right, will go down to the to the U channel, the surface channel, and discharge away, right? So anything falling, right, any rainwater falling on the slope will be discharged as soon as possible, rather leaving the heavy pour, right, dripping along the whole slope, right? We want to here for this part will be discharged by this channel, right? And for the upper part or individual part will be discharged by the the channel here, right? So we divide the slope surface into several parts, right? Instead of one. So that will facilitate the drainage of the any discharge, right? Any rainwater falling on the slope surface. Okay, stability of slope. Say for a slope, for a certain height. Now there are two important parameters for the slope. First of all, is what? The height of slope. Right? The height and then what? The angle, right? The angle here, theta, right? Height of slope, sorry, and the theta. If the height of slope is very high, if the height and the theta is very high, in other words, you have, sorry, a very high slope and the angle is very steep, right? If this h is increasing and the theta is increasing, then the slope is very dangerous.
Hi, sir. Hello.
Unstable.
Hi, sir. Hello. Hello.
So try to prevent a very high slope and also a steep slope.
Sorry to interrupt.
Hello.
The screen still freezing in the shutter phone.
Okay, it's almost 8:30, right? So I give you 10 minutes break before we start our tutorial, okay? So we'll come back 10 minutes later, okay? Let's take a break. So 10 minutes break.
Chúng ta hẹn mà chào với chị Phi như đi thì đâu cầm à.
Are you all back to the tutorial and the lecture? Please respond me if you are in. 1, 2, 3, 3 only, 4. Okay, now I don't want to reiterate, right? Repeat the whole thing again. So I show you the slides where I have put down, the mark, the graphics and so on. So can you take a photo of the presentation slide? I think that should be good enough because, that is, the common knowledge, right? For the slope. So I don't want to repeat everything. Is that okay? So the next slide is here. The berm, right? We'll talk about the berm, the surface channel. And the dotted lines are the rainfall. So the important parameters for a slope, the h, the height of the slope, and also the theta, right? Greater the theta, greater the h, it will be more unstable. Okay, let's take a break there, right? So we will go back to our tutorial. Now, before we, okay, let's take a check first. Can you see the tutorial assignment submission, the instruction for your submission? Can you see? Can you see the Word file? Yes or no? Now, your submission should be in the form of a single file. Do not give me several images or inside your email message, right? I want a file only, right? In PDF format. And it should be attached to your email. Now, do not direct me to any SharePoint or any cloud, right? I'm completely lost, right? I cannot hold on your assignment. Please just write a normal email with an attachment, right? The attachment is a single file in PDF format, not in Excel form or any others, right? And your file name should be looking like that. Assignment 3, A3, right? And then Chen Diamond, your name, and then still number. Now, if you do not follow this format, now you are wasting my time, right? To put everything, right, in a uniform manner. I want everything, in a neat and tidy and in a uniform and consistent format. Okay, that's my requirement. And your submission should be in time. An email to this, right, official email address in the university. Is that clear? Okay. Now, please do not let me waste a lot of time in compiling your files, right? Sometimes I have to combine several files into one. You know, that's not effective, right? In terms of engineering. I think I have told you, right, in the last, tutorial session, that everything should be in uniform manner, right? In a uniform and consistent format. Okay? So let's just cooperate each other, right? Now you need to return your assignment 3, right, in the next week, right? So you have exactly 7 days, right, to complete your tutorial assignment. There will be no solution provided, right? Because you have to hand in your work, assignment 3. Now the topic is on the lateral earth pressure, but forget the site investigation. We purposely pick up the question 4, right? So you need only do the 3 questions, right? 3 questions for this assignment. There will be no question set on the site investigation. Now let's take a look on the question 1, Q1. Right? Now here is the smooth and unyielding wall. It means a very rigid, and there will be no friction between the soil and the wall, right? So it's a smooth wall. So that means the Rankine pressure theory could be applicable here. And then you have a wall height of 3 meters, and then you have the soil here, gamma 16.5. So you have the soil properties here, right? Gamma 16.5 km per cubic meter, and the friction angle 30 degrees, and cohesiveness means what? C is 0, right? No, you have no cohesion. Okay, and that's the GWT, groundwater table, right? Groundwater table at 1 meter above the base of the excavation. So what you're going to do is draw, right, the earth pressure diagram, and then find the total lateral force and the location of this force, right? These are nothing as important as this word. What does that mean? Low lateral earth movement or wall movement, right? It means it is at rest. Okay, so here are the keywords, right, for the problem, right? The wall is at rest, and you are given the soil properties, and then you have to draw, first of all, the pressure diagram and the total force and the location of the force, and given that the groundwater table. Okay, So you have the effective stress, okay, and then you plus the U equals the total stress, okay, effective stress, and that is the water pressure before you get the total pressure, right? Okay, what's the effective pressure? And then you have the, sorry, and then you have the pore water pressure, right? Plus. It should give you, okay, that's the total pressure, right? Sigma dash, and you got the U, and that's the total pressure. Can you calculate? That is the A, okay? If that is sigma B dash, can you get the value sigma A dash? Is equal to K naught, right? Times gamma Z, right? Because that is the vertical pressure. And then that is the K naught because it's less. What's K naught? 1 minus sine phi, right? So 1 minus sine 30, right? Sine 30 means 0.5, right? So 1 minus 0.5 equal 0.5, right? So equal to 0.5 gamma. What's gamma? 16.6. Sorry, 16.5. What is that? At the point A, the Z is equal to 2, right? So it gives you exactly 16.5 kPa. Okay. Now what about B dash? K sigma, sorry, sigma A dash. What is sigma B dash? K naught. Okay. Now effective stress. So you use what? The gamma dash is equal to 16.5 minus the unit weight water, right? And times what? Is it correct? What's the vertical stress there? Now, tell me what do you know about the effective stress at this point? Oh, sorry. What's the effective stress here? What's the, K dot? What's the total stress there? Remember, right? the stress is equal to the gamma Z, right? You have to add the individual layer, right, stresses together before you go to the bottom, right? So layer 1, if that is the layer 1, and that's 2, so K naught times, the gamma Z, right? So equals to what? 0.5. So you all are staying here, right? And can you follow my explanation? Yes or no? I don't want any disconnection, right, in between before I proceed on. Is that okay? Okay, that's good. Okay, now, so you have to add the stress, right, from layers to layers, right? So starting from the top, right, and then you come up here, right? So it is, we have done that, right? 16.5 plus what? That's layer 1. And the layer 2, what's the layer 2? Because we are talking about the, the effective unit weight minus 9.81. That's the gamma, okay? That is, the gamma dash times what's the thickness of the layer 2? 1 meter, right? 1 meter, okay? Sorry, here. Gamma 16.5 times 2 meters, right? It's 2 meters plus, gamma here, right? Plus 16.5 gamma times 2 plus times 2, right? Plus, okay? And that is, gamma Z, right? So you got here, right? So that is the layer 2, right? So that's the layer 2. Okay, layer 1, 16.5 times 2 plus the gamma dash times the, the thickness of the second layer. So you got what? 19.845, right? kPa. So you got here, right? So that is what? 16.5. And here you got what? 19.845, right? And what about the U here? The water pressure. the water pressure. What's the U there? What's the U here? The UB, right? The pressure, the water pressure at the point P, U, the water pressure at the point B, 9.81. What's the depth of the water? 1 meter, right? So equal to 9.81 kPa. So we write it down. One here, right? So you got the effective stress and also the pore water pressure. So what's the total pressure here? 16.5, right? And then what's the total stress at the bottom? 19.85 plus 9.81. It gives you what? 29.66, right? So that is the result for your so here, right? Is the total pressure diagram. Okay? Is that okay for you? K naught is the pressure coefficient at rest. K naught. You know K naught? Because whenever you calculate the gamma Z, it's the vertical stress. So you have to multiply K naught with the vertical stress to get the horizontal stress, the lateral earth pressure. Now that K is equal to 1 minus sine phi, right? Equal to 0.5, because the data given by the problem is that the wall is at rest, right? So you have to use K naught. Is that clear? Mr. Lam? You got it? So in other words, I know that your question. So okay, I make the amendment, right? I should not put down the 0.5 there. K naught is equal to 0.5. Okay. Sorry for that. So what about the others? Do you understand? What were the others? Now, if then we will proceed on, right? The calculation. Okay, I will continue the other parts of calculation. Now, of course, I will not compose solution for you because it's your job, right? But for some hints, right? You have divide these two into 4 parts, right? So for the, you want to calculate the force F1, that's F1, and here the center here, right? That's F2, and here again you got not the F3, right? So what's F1? It's equal to the area of this triangle, right? Okay, and what's F2? Is the area of this what rectangle. F3 is equal to the area of this triangle. Okay, so you can easily work out the area of these components, right? So you got F1. Now you know this the centroid where the F1 will be acting is equal to what? Is equal to 1/3, right? Of this height, right? So you got the position of the F1 and also the F2 is equal to the center of the rectangle, right? The height of this F2 above the bottom, and also the location of F3, right? Above the bottom. So what's the total force? What's the total force? F1 plus F2 plus F3, right? So that gives you the total force. And what's the location of this force? It's equal to, by taking moment about the, the base, right? So divided by the total force, right? It gives you the height of the final resultant force. Okay, take moment about the bottom. So okay for Q1. Any question for Q1? Response, please. No question. Okay, good. Okay, for question 2. Seems the computer respond very slowly. Maybe quite a lot of users, right, are using the blackboard at the same time. For question 2, now you are asked to derive the expression for the Rankine passive lateral air pressure. So in other words, if you consider the soil element here, you are okay. That is, the shear stress, and that is the normal stress, and you have, the soil element here, this sigma. Sorry, that is sigma Z. So that is the sigma Z, and because it's the wall is moving inwards, so you need a larger pressure, right? The sigma X. So sigma X should be greater than the sigma Z, because when the wall is trying to press inwards, the horizontal pressure will grow, right? Will become larger and larger. So eventually, the sigma X, the horizontal stress, is much greater than the sigma Z, until the Mohr circle touches the failure envelope, C plus sigma tangent phi, right? And here, so you got what? The C here, right? And you got the radius here, right? Okay, that's the Mohr circle touching the failure envelope. And what's this angle? Phi, right? So how are you going to derive the expression? Now you have to use mathematics, right, to perform the proof. Here, what's the length here? It's equals to C over tangent phi, right? And then, what's the coordinate here? The center is equal to the, sigma X plus sigma Z divided by 2, right? Okay? So consider this right angle triangle. So what's the relationship between the R and this length, right? The hypotenuse of the right angle triangle. So simply C over tangent phi plus sigma X plus sigma Z divided by 2 equals to what? R over sine phi, right? That's R. That's the R. So R over the hypotenuse is equal to sine phi, right? So that's why the hypotenuse, right, here, the length here, is equal to R over sine phi, okay? But what's R? What's R? R is equal to what? Sigma X minus sigma z, right? So when sigma x minus sigma z equals to 2r, right? Divided by 2. So that is the r, right? Sigma x minus sigma z over 2 is the r. And then write down the psi phi, right? Now, can you rearranging, right, the sigma x in terms of sigma z? Now try to get the expression. Try to get the expression. Sigma z in terms of, sorry, sigma x when you put everything sigma x on the right hand side and put all the things on the right hand side, you will come up with what? Sigma x equals to 2c, right, cosine phi over 1 minus psi phi, right? And then plus sigma z 1 plus sine phi 1 minus sine phi. Okay? And then you have to use this formula. The compound angle, right? Compound angle formula. Cosine phi 1 minus sine phi is equal to tangent 45 degrees, right? Plus phi over 2. So you put it back, you will come up with the, the final equation. Now I will leave it to you. That will give you what? The sigma x is the passive pressure, right? Should be equals to, right, Kp gamma, sorry, okay, Kp, okay, sigma z plus 2c square root Kp. Okay, of course, what is Kp? Kp equals to 1 plus sine phi, 1 minus sine phi, okay? Or equals to tangent square 45 degrees plus 5 over 2. Okay? So that are the main step. How can you derive this expression, right? So any question for this deduction of this formula? Now I give you the hint, right? To consider that right angle triangle and the coordinate of the center of the Mohr circle. Now, by combining these two things, you should be able to derive that expression. Of course, with some subtle mathematics knowledge in the compound angle formula, then you should be able to derive that expression. So is that okay for you? So any question for question 2? Good. So you should be able to handle that, right? Now come back to the B part. It's quite straightforward, right? For the part B, for the part B here, right? Given that phi equal 25 degrees, right? And C dash equal to 0, and gamma is 18.8, right? Kn per cubic meter, and H equals to 7 meters. So can you use that equation, right, to determine the total lateral force? Okay. So what's Kp? Kp. One plus sine phi, right, over 1 minus sine phi. So 1 plus sine 25, 1 minus sine 25. So you got something like that, right? And then what's the sigma z? Vertical stress, if that material is 7 meters, right? You got this Kp gamma z equals to Kp, right? If that is, that's a Kp times what? 18.8, and then times gamma h or the z equal to 7. So you got this value, right? So you got the sigma z. So what's that bottom? The bottom stress is equals to what? Kp times sigma Z, right? Okay, so Kp is a question mark times, sorry, that is already, that is B already, right? Because that is, you know, the Kp, right? That is the Kp times the vertical stress give you this double question mark is the bottom stress. Once you got the sigma B, so can you find the force here? So F equals to what? Times the area of the triangle, right? Times 7/2, okay? And the bar H is equals to 7/3. So that's the location, right? That's location of the resultant force. Okay. So that is the solution for the question 2. So any question for the question 2? Now for the question 3, I think you should be able to do that because we have done a similar one in the lecture notes, right? When we are discussing the, you know, the Z0. You know, the tension cracks. Remember that? The tension cracks. Okay, remember that? Right. Here, right? You got, you know, that is the Z0, right? Okay, that's the tension cracks. Crack there, right? So you should be able to work out this question. Okay, that's all. That's all I'm going to work out with you in this evening. So you got any question? Sorry for running over time. So you should be able to do the, you know, the whole set of questions under the assignment 3. Is that true? It's not that difficult, right? You should be able to work out the, you know, the vertical stress and horizontal stress according to whether they are in the active or in the passive condition and so on, right? So I will leave you soon if you have no problem. Let's end up our lecture and tutorial in this evening, okay? If no question, then good night, everybody.